Hello all, I am Pradeep from the Department of Electronics Engineering. Today I will be presenting a foundational topic coordinate system in the study of electromagnetic waves. Understanding these systems is the first step in solving complex field equation as the choice of the coordinate system can significantly simplify the mathematical workload depending on the symmetry of the problem. So in electromagnetic waves, we primarily work with three orthogonal coordinate systems. They are Cartesian coordinate system, cylindrical coordinate system, and then spherical coordinate system. Cartesian coordinate system is also known as rectangular coordinate system, which is the standard for flat or box-like geometries. And the next is cylindrical coordinate system, so which we'll be using for problems involving cables, wires, or any axial symmetry. The third one is spherical coordinate system, which is essential for point sources, antennas, and radiation patterns. So in Cartesian coordinate systems, this system it is defined by three independent variables x, y, and z. Here, each variable is unbounded, ranging from negative infinity to positive infinity in both the directions. So x tends from minus infinity to plus infinity, similarly y and z also. And then the unit vectors are ax, ay, and then az. These unit vectors are constant in both magnitude and direction throughout all the space. And the next is differential displacement, that is dl. So it is a vector distance between the point p of x, y, z and the nearby point q of x plus dx, y plus dy and z plus dz. So it is defined as dl is equal to dx ax vector plus dy ay vector plus dz az vector. The next one is differential normal surface area ds. So it is defined by keeping one coordinate constant. So by keeping x surface as constant, ds is defined as dy dz ax vector. And then by keeping y surface as constant, dx is defined as dx dz ay vector. And then similarly by keeping z surface as constant, ds is defined as dx dy az vector. The next is differential volume. So this infinitesimal volume formed by the intersection of these three differential lengths, and it is given by dv is equal to dx dy and then dz, and this dv it is a scalar quantity whereas dl and ds is a vector quantity. Then the next one is circular cylindrical coordinate system. So it has three variables rho, phi and then z. So this system is ideally suited for problems with axial symmetry as I told already, such as analyzing the fields around the straight wire or within a coaxial cable. So here the variables involved, that is rho, phi and then z, or varies from rho varies from 0 to infinity, and then phi varies from 0 to 2 pi, and z varies from minus infinity to plus infinity. So here rho is the radius, that is perpendicular distance from the z axis, and then phi is the azimuthal angle. So this angle is measured from x axis in the xy plane, and then z is a height. So it is identical to the Cartesian z coordinate. Here the differential displacement dl is, unlike Cartesian coordinates, a change in angle d phi results in an arc length of rho into d phi. So the dl is defined as d rho a rho plus rho d phi a phi plus dz a z. And then the differential normal surface area. So here by keeping rho as constant, that is cylindrical wall as constant, ds is defined as rho d phi dz arrow vector. And then similarly by keeping phi as constant, ds is defined as d rho dz a phi vector. And then similarly keeping z as constant, ds is defined as rho d phi a z. And then the differential volume dv is defined as rho d phi d rho and then dz. So in order to convert the cylindrical coordinate system into Cartesian or vice versa, that is from Cartesian to cylindrical, the coordinate transformation involves x is equal to rho cos phi, y is equal to rho sin phi, and then z is same as that of in both the coordinate system. and then the rho is equal to square root of x square plus y square, and then phi is equal to tan inverse of y by x, and then z is same. The next one is spherical coordinate system. The spherical coordinate system is used for problems with point symmetry, such as calculating the radiation from a small antenna or the field of a point charge. So here the variable definitions involves r, theta and then phi. R is the radial distance, that is distance from the origin, and then here r varies from 0 to infinity, and then theta is the co-latitude angle. So this angle is measured from positive z-axis, and this theta varies from 0 to pi, and then phi is the azimuthal angle, the same angle as it is in the cylindrical coordinates, and it varies from 0 to 2 pi, and then the differential displacement. So this system involves two different arc lengths. A change in theta creates an arc of r d theta, and a change in phi creates an arc of r sin theta d phi. So dl is defined as dr ar plus r d theta a theta plus r sin theta d phi a phi. And then differential normal surface area by keeping r, that is spherical surface, as constant. Ds is defined as r square sin theta d phi r vector. And then by keeping theta as constant, that is conical surface, ds is equal to r sin theta dr d phi and then a theta. By keeping vertical plane, that is phi as constant, ds is r dr d theta a phi. The next is differential volume. So this volume element, it is a product of three differential lengths. So it is defined as dv is equal to r square sin theta dr d theta d phi. And then the coordinate transformation from Cartesian to spherical involves x as r sin theta cos phi, and y as r sin theta sin phi, and z as r cos theta. And then r is defined as square root of x square plus y square plus z square, and theta is tan inverse of root of x square plus y square by z, and phi is equal to tan inverse of y by x. Thank you.